All right, we're live. If anyone is online, can you let us know you're there with a question? I'm going to go ahead and get started though, but please do let us know that you're live. Okay, so last class, we dove into the central limit theorem, which is going to form the basis of today's class, confidence intervals, as well as the next few classes on confidence or on hypothesis testing, the t-test, and all of that. So we're going to start out with a review of the central limit theorem again, just to make sure that you're comfortable with it. And then we'll talk about confidence intervals for a population mean and proportion. And I'll have some results from the few of you who filled out the survey today before my cutoff time, that when I could still get things into the lecture. Good. Thank you, Eddie and Danielle. So this is going to be a mostly conceptual class. I guess all of them are, but I'm really going to focus on interpretation of the confidence intervals and being able to relate them to different confidence levels, to sample sizes, and other population parameters. So hopefully you'll have a good understanding of all of those things by the end of today. So just a reminder of some of the stuff from last class about the central limit theorem. Key to that was the difference between the population and a sample, and especially between the population distribution and a sampling distribution. And you'll recall that the population is made up of individuals, and it's all of the individuals of interest for a particular study. A sampling distribution is made up of summaries of samples. So a sample might be a sample of 30 people or 100 people, but in the sampling distribution, it is about a bunch of samples, all of the same size. So if n equals 30, it's many samples of size 30, and it's a distribution of the means of those samples. And we use that distribution of the samples to make inference about the population from just one sample by estimating the probability of obtaining a sample that of properties like we described for a given population. And we'll be using that today for our first bit of inference through confidence intervals. Recall the notation. We're using Greek letters for the population. So mean and standard deviation are mu and sigma. I like to use capital letters when we're talking about proportions, capital P, capital Q, instead of using Greek letters and then using the lowercase of those for samples, largely because it's a hassle putting little hats over the P's and the Q's. You will often see hats put over things that are estimated from a sample. So you'll see a P with a hat on it. I think Tony likes to do that. That is common as well. But the important thing is keeping in mind whether something is a fixed value of the entire population, something that we only know in theory, or if it's something that we're estimating from a sample. The central limit theorem was all about the relationship between the population distribution and the sampling distribution. So given a population distribution, such as of serum cholesterol of individuals, or we did ages or running times of runners in a race, if we know the mean and standard deviation of that population, we can convert that to a mean and standard deviation of the sampling distribution. And you remember what that standard deviation of the sampling distribution was called? Standard error, exactly. And is standard error bigger or smaller than the standard deviation of the population? It's smaller, right? Only in the pathological case of n equals 1 would it be the same. Because then your sample is actually an individual, so it's a direct estimate of the population standard deviation. But in all normal samples, n is always greater than 1. The standard error is always less than the standard deviation. And that was intuitive, right? That made sense. Does anyone remember why that seemed intuitive? Mm-hmm. Exactly. You have less variation in the means of groups of individuals than in the individuals themselves. So in a group, when you take the average, you lose the individuality. You're just looking at group averages. So the variability in group averages is less than the variability in individuals, and that makes sense. All of the inference that we do in this course, and for the most part in statistics, is about group properties, group averages, group proportions, things like that. So it's about the behavior of groups. Yes?
I just want to make sure I'm not going to repeat it.
Yep.
Variability in group averages less than variability in individuals, you said?
Yes, the variability in the average is less than the variability in the individuals. We've got plenty of time today, so don't be afraid to interrupt and ask questions and reiterate things back to me. I want everything from today to be very intuitively obvious to you by the end. And keep in mind that, as you know maybe by now, on the exams, I do like to make sure that a certain amount of it is just testing your intuition. Not, there is a certain amount where you have to calculate stuff, but a significant amount of it is, do you have a good intuition for this? Because that, I think, is what you're going to take forward into the future. After you forget how to calculate a confidence interval, you'll at least, you'll remember what it means and be able to look at them and understand what they mean. So the three components of the central limit theorem, and these, remember the CLT, it relates to the population distribution to the sampling distribution. The first one is that the means of those two distributions are identical. So the mean that we have from the sample is the best estimate that we have for the mean of the population. And if we took many, many samples, the mean of those samples would be identical to the mean of the population. So if we have a few samples, that mean is approximately the same. If we have many samples, so that we have the entire sampling distribution, they're identical, right? Yes? So the bigger the sample, then the closer one measurement will be to them being, or one sample, the closer its mean will be to the population mean. For the distribution, it doesn't matter what the sample size is. For any sample size, the mean of the sampling distribution will be identical to the mean of the population distribution. But of course, for large N, the standard error gets smaller, so the mean of a single sample will be closer, on average, to the population mean. Part two is this formula that you'll get very used to that relates the standard deviation of the population to the standard error by this factor of the square root of n. Yes?
So this is back to this question and your answer to that question. When you say with the sampling distribution, it doesn't matter what n is, the mean is going to be equal to the mean of the population. What determines how many samples are in a sampling distribution? Does that matter?
So
in the distribution?
the question is how many samples go into the sampling distribution? And the answer is, for a smooth line like that, it's an infinite number of samples. You can approximate it with any large number of samples. Like I gave some examples in the last class where I plotted histograms. I took 1,000 samples to make one of those histograms, and that looks pretty accurate to what the sampling distribution really looks like. But the central limit theorem is in the limit. It's for any n, so any sample size, but it's in the limit of an infinite number of samples. So when you hear infinite, just think large enough, just think big. And it's a theoretical result, but it's very useful in the practical case where we only have one sample. It's kind of derived under the assumption that our one sample that we took is just one of an infinite number of samples that we might have taken if the universe had been slightly different. So due to that part 2, it allows us to convert the population standard deviation to the standard error. And it means that as n increases, the standard error must decrease. So if n quadruples, the standard error, shout out. What happens if n quadruples? Yeah. The standard error decreases by how much? Not 1/4. Yeah, by a factor of 2. So if you go to a 4 times larger sample size, your standard error will be half as much as it was. If you go from n equals 10 to n equals 40, you get half the standard error. If you go from, I don't know, increase by a factor of 16, like from n equals 4 to n equals 64, then you get a 4-fold reduction in your standard error. And of course, as a result of this decreasing standard error, then for large sample sizes, the mean of any one sample is likely to fall closer to the population mean. And this is kind of an essential prelude to the confidence intervals that we're going to do today. That the larger your sample size, the more confident you can be, the less uncertainty there is about what the population mean is. We're going to be taking one sample and then making inference about a plausible range of means for the population. This, well, very similar formula applies to proportions. So you should be able to apply all these same principles to proportions as well, at least as long as the sample size is large enough. There is that approximate rule of n equals, or p greater than 0.05 and 1 minus p greater than 0.05, as long as, p times n greater than 5 and 1 minus p times n also greater than 5, then you can apply these same principles to the proportion, because we use a normal approximation to the proportions. Yes?
One good statement you made, if you can just repeat again. So you said the n allows us to calculate the standard deviation in reference to.
And n allows you to calculate the standard error in reference to the population standard deviation. Yeah. If you have any two of those three, you could calculate, well, you can estimate the population mean from, here just a sec, sorry, so from this formula, standard error equals sigma over square root of n. You can calculate your standard error from the population and n, or calculate any missing one of those three. So with these things together, and I guess I didn't write down the third one, but that was that for a sufficiently large n, so each sample, if each sample is large enough, then the sampling distribution will be normal, no matter what the population distribution is. So we saw examples of weird triangular shaped population distributions, whatever it is. If n is large, like greater than 30-ish, the sampling distribution will be very nearly normal. Now, if the population distribution is normal and n is small, say n is 3, what can you tell me about the sampling distribution? What distribution is it? So I said that part 3 of the central limit theorem was that if we have a large n, let's say n greater than 30, for any population distribution, the sampling distribution is normal. Now, what if n is small, but the population distribution is normal? So it's weights. Weights are normally distributed in our population. We take samples of n equals 4. What's the shape of the sampling distribution going to be?
It won't be symmetrical, it'll be like skewed.
No, it'll be symmetrical. Yeah, it's actually going to be t-distributed. It's a bit of a trick question, and we'll get to that next class. So if n is large, it's normally distributed. If n is small and the population is normally distributed, then the sampling distribution will be t-distributed, just as a bit of a preview. And so just as a reminder on the bottom here, the standard error, it's just the standard deviation, but it's the standard deviation of the sampling distribution. So it gets this special name, the standard error, so that you don't confuse it with a regular standard deviation. Usually when you talk about standard deviation, you're talking about like the variability in heights, weights, running times, ages. The standard error isn't a variability of any of those things. It's a variability of samples, of sample means, right? Or sample proportions. And we're going to use this for calculating confidence intervals. First, some terminology. A point estimate is a single number, and usually it is our best guess at something. It's our best guess at a population parameter, or it's our best guess at the true answer for something, if there is such a thing as a true answer. In our example of guessing the age, your point estimate is the age that you think I'm most likely to be. But it doesn't give you any idea of the uncertainty, right? It's just your best guess. So someone who you know very well but you can't quite remember their birthday, there's less uncertainty. Someone who you've never even seen, there's going to be a large uncertainty, right? I mean, you could take a good guess that anyone in the world, even if you don't even know anything about them, they're going to be between 0 and 120 years old with pretty high confidence. Whereas someone you know well, you can put a smaller interval on that with the same amount of confidence. So that interval estimate, yes, question? No, a point estimate's a single number. So that would be an interval estimate. That's a range. So that is an expression of uncertainty. So interval estimates are an expression of your uncertainty. They give, right, that's right. Point estimate is 39 years old. Interval estimate is between 30 and 50 years old. So the interval estimate, it has a middle, which is probably where you think the answer most likely is, not necessarily, but it also incorporates something called a margin of error, and that is the amount of error on either side of a point estimate that you consider to be plausible. Yes?
So for this example, then technically what you're saying, we're just guessing, it doesn't even matter what the real number is. So in this case, we won't actually know what is the real age, because we're just estimating a point or estimating an interval.
Yeah, so the question here is about, is that, or it's a comment, I guess, that you don't know the real age. So your point estimate is just a guess, and your interval estimate is a range of plausible values. And that's an interesting point, because if you actually knew my real age, then the whole exercise is moot. You don't bother with any of it. You don't need intervals. Your point estimate's not an estimate, it's the answer. So all of this is about expressing uncertainty when you don't know the real answer. All right, oh, wait a minute, how did this end up in here? It didn't sync up. This is last year's survey. Let me see. Let me see if I can get our new 507. Oh yeah, there we are. So the handouts look like that because that was last year. I got it out a little earlier last year and there was better participation. I only got 6 of your answers before I had to finish making these slides today. So I like this exercise because it gets you to think about how to put an interval around your point estimate. And we can actually look at each one of these and think about what was the thought process behind these intervals. So they're organized here from oldest guess to at the top to youngest guess at the bottom. And I've plotted in dark bold the 90% confidence intervals, and in dashed lines the 50% confidence intervals. So in case you didn't see the survey questions, the questions ask, first of all, what's your best guess? And that's what I've put as a dot here. That's the point estimate. And then I asked for the upper and lower bounds of the interval in which you're 50-50 confident of my true age, and the interval in which you're 90% confident of my true age. So let's look at some of these. Let's look at this first one. This guess was 41 years old. The 90% confidence interval went from 40 to 42, and the 50% confidence interval went from 36 to 44. So there's thing that doesn't make sense in this answer, and there's also another part that does make sense. Does anyone want to comment? Yes.
Well, I had to think about that too. Initially, I put the smaller range for 90%, but you should be more sure that the age is in a bigger range.
That's right. You should be more sure that the age is in a bigger range. What were you going to say? Yeah. That's right. If you give a big range, you can have more confidence in it. You know, so if you're betting, you could give better odds to someone by giving them a big range. Like, it's a common misunderstanding. I've seen it in, like, I've given similar surveys in different classes, and it is a common misunderstanding. I think that part of the misunderstanding comes from another way of thinking about confidence. Like, if you think of confidence as being how confident am I in my answer, then if you have high confidence, you should be able to say, you know, he's between 40 and 42, and if you have low confidence, you have to give a larger range. But that's not what the confidence interval means. What you're actually talking about in that case is the amount of information that you have. So if you have more information for the same level of confidence, you can give a smaller range. If you have less information, you have to give a larger range for the same level of confidence. Confidence would have to do with betting, for example. Like, if you have an accurate 50% confidence interval, then you can give even odds to someone that the true answer is in there and come out even. If you have a 90% confidence interval that is accurate and you give even odds, you're going to come out ahead. So there's also something that does make sense about this guess, though. Does anyone want to say what that is? Another feature of the relationship? Yeah. Their point estimate is right in the middle. Yes, which I think makes sense. I mean, it doesn't have to be that way. Maybe you have more uncertainty on one end than the other, but commonly your point estimate is going to be in the middle. So what about this second one? Yeah, I think it makes perfect sense. This second one, you know, we have the point estimate in the middle. We have a 90% confidence interval that's larger than the 50% confidence interval. Looks good. How about the third one? What's that?
Bad guess.
Yeah. Right. Yeah, their point estimate should be in there 90%. That's another point. If you look at the width of these two, they're almost the same. Yeah. So it just got, like, the 90% confidence interval got shifted over. So I don't know. These were anonymous. I have no idea who they were. But if this was your answer, then you should think about confidence intervals some more, because yeah, there's no way that your confidence interval should not include your best guess, because it's a bad confidence interval then. If your best guess is lying outside of the range of plausible guesses, that's a problem. And if you're giving the same range to be 50% sure as to be 90% sure, that's also a problem. That means that you're not actually adjusting for different amounts of confidence. So this looks good too, right? They just think I'm a little younger. Yeah. Your point and your point estimate should be within any confidence interval. It doesn't matter what the level of confidence interval it is. It must contain your best guess. It's an illogical confidence interval if it doesn't contain your best guess.
Your point estimate fall in your 50 and your 90%?
Yes.
Like the growing.
Yes, your point estimate should fall in your 50% estimate, your 50% interval, your 90% interval, your 99% interval, any interval. Your point estimate must fall inside it. And for a symmetric distribution, it should be in the middle. You can imagine if the sampling distribution were asymmetric, then maybe your point estimate wouldn't fall right in the middle. But if the central limit theorem holds, if it's a large sample, or we have a normally distributed population, your point estimate will fall in the middle of any confidence interval that you construct. Let's see. Actually, it's a nice thing about having not too many responses. We can look at each one of them. How about this one? What's that?
Like the whole 20 years of 9% confidence interval.
Yeah.
Covers all bases.
Yeah. I mean, so that, I mean, that's good that the 90% confidence interval is bigger. It reflects little knowledge or basis on which to make a point estimate. So that's a valid confidence interval. It just means that you don't have a lot of information.
In this case, so then the person, instead of having the point estimate in the middle, they actually started.
Yeah.
For the 50% from their best estimate.
Yeah. That's right. Yeah. So the point estimate's not in the center of that 90% interval. And I think, there are situations where that makes sense. In this situation, that might make sense. You're not going to calculate a confidence interval that ends up like that. The ones you calculate will be centered on the point estimate. But, maybe here someone has figured, well, he can't be less than 30 because he's got a PhD and he's a professor now. You can't be less than 30. But I have no idea how old you are. Yeah.
Professor, in that case, too, let's say we take that into consideration. Does that mean it's some kind of bias in there that we're trying to shift? We're basically going by no knowledge, right?
Yeah. So is that bias that you're going by no knowledge at one end of the spectrum? I mean, in a way it is, because there's some certainty in your knowledge, and confidence intervals. Well, at their most basic, a confidence interval is just the interval in which you can have a certain level of confidence of the true answer. And in that sense, no, it's not biased. However, the fact that the point estimate is not in the center, how can I say this? It's a form of bias, just in that it's saying that we have more knowledge about one end of the plausible values than at the other end, if that makes sense. Yeah, again, in this class, you're going to take when you're calculating confidence intervals, you're going to take your point estimate, you're going to add and subtract the margin of error from it, and it will be symmetric. But in general, there's nothing wrong with having a point estimate that's off-centered. And of course, here the 50% confidence interval, funny, in that one, it ends at the point estimate, which, I mean, I guess a case like that could happen if, I don't know, there were, what happened 35 years ago, or I don't know, if there's something where, you know that I could not be less than 35 years old, but that was still your best guess. I don't know, it's a weird situation, but in this last one, that looks fine, right? So do all of the confidence intervals? Yes. Just because they're kind of numbers that are easy for people to think about. I don't know. No, not really. I mean, those are not usually the ones that we use in public health. Usually it's a 95% confidence interval. Sometimes it's a 99% confidence interval. But you'll be able to calculate any confidence interval after tonight. So I guess most of these made sense, a few of them didn't. Which is larger, the 50% confidence interval or the 90%, which should be larger? 90, yep. Are people with larger intervals, so if two people have, if they're 50% confidence interval, if one of them has a larger 50% confidence interval, is that person more or less confident? And this is getting at that confusing interpretations of the word confident, and I kind of intentionally used it in this confusing way here. Yeah, they're less confident because we're comparing the same confidence interval. So usually I prefer to avoid using the word confident for that reason there, and say, are they less certain, or do they have more or less information? In this case, you all have basically the same information, so it does have to do with your, maybe it has to do with your innate sense of self-confidence. Maybe some of you have training at age guessing, I don't know. And the point estimate typically is going to lie in the middle, but it definitely must lie somewhere within the confidence interval. So maybe I should send out another survey afterwards and have you guess my weight and plot that and see if if everyone makes sense. I will. At the end of class to keep you all listening. Actually, it's occurred to me that based on your sample and last year's sample, I could use it for hypothesis testing too, and test the null hypothesis that I'm not aging. So in this example, you constructed a confidence interval based on your past experience of people whose ages you knew and applying that to me. That's when we do this in class, when you do this in research surveys, you're not just going to guess a confidence interval, you're going to calculate it from a sample. You're going to take a sample from a population, calculate, you're going to estimate the population standard deviation, you're going to estimate the standard error, and you're going to use that to construct a confidence interval. So it's just based on the data. And I'll do that later too with with your survey as well. So in order to construct that confidence interval, you first need a point estimate. And remember that because the mean of the population and the mean of the sampling distribution are identical, the best guess, the point estimate, is going to be the mean of our sample. So you take your sample of n equals 30 or whatever, you calculate the mean, that's your point estimate. So it's your best guess. Even though you know it's not exactly correct, it's the closest guess you can make. So if I were doing that with the age survey, I would just take all of your point estimates and I would average them. And then we're going to use this central limit theorem and that part 2 that related the standard error to the standard deviation and calculate a margin of error. And I'll show you how to do that. So the margin of error is how big the confidence interval goes above and below the point estimate. So this is just an example of a 95% confidence interval. It's how far above and below 95% of the probability in the sampling distribution lies. So from the central limit theorem, you learned how to get the sampling distribution from the population distribution. So the middle of the sampling distribution is at x bar, the mean, and the standard deviation of it is the standard error. It's that sigma over square root of n. And all you have to do is a lookup in a z table for now, and to see how far above and below your point estimate you have to go to get 95% of the probability in your sampling distribution. That means that if you took an infinite number of samples, 95% of them would fall in this shaded area. Yes? You could use the empirical formula too. Yep. Yeah, you can use the empirical rule for the 95 or the 99 or the 60, the 66% confidence interval, or you can use a z table for other values. So you can do this, and as long as either n is larger than 30, so you have a large sample, or the population is normal and we know the standard deviation of the population. So that's a key distinction there, whether you're using the known true population standard deviation or whether you're estimating it from a sample. And when you have a small sample that you estimate the standard deviation from, that's when we're going to get into the t-distribution next class. But I didn't want to cloud your heads with additional concepts today. Just focus on the main concept of estimating an interval from a sample. So here is your basic formula for, or recipe for calculating a confidence interval. And I believe I've put on YouTube in the mini tutorials section a little section on how to calculate a confidence interval by hand. But you take your sample mean, and then for a 95% confidence interval, it's plus or minus 1.96 times the standard error. For 99%, it's 2.58. Does anyone know where you would get that from if you didn't get it from this slide? Where would that 2.58 come from? Yep, the z table. So we would want the central area of the z table that contains 99% of the probability. So if it's a left-tailed z table, it would be the value of z for 0.995, because it would be 0.005 of the probability in the right-hand tail alone. We could look that up right now. I think I have handy the textbook. Distribution tables. So I'm going to look it up under we can use the negative z, it doesn't matter. We want a probability of 0.005 under the left tail, right? Because if we have 0.005 under the left tail, there will be 0.005 under the right tail for a total of 0.01, which means 0.99 in the central part. So, see, I'll make this a little bigger. Okay, starting here, that's too small. Just gonna go down, 0.006. It's a little too big, let's go here. Oh, right there, so it's about minus 2.57 or minus 2.58. And what did we say on here? 2.58. Any questions about that? No, we're good. You don't need to think too much about the computational aspects of it. You'll do lots of that in the lab and in the assignments and preparing for the exam and everything. The main point now is that you understand what a confidence interval is and where it comes from. So this is the general idea that you take your, if alpha is 1 minus your confidence level, then you look up the z value for alpha over 2 and multiply that by your standard error to get your margin of error. And it's the same thing whether we're talking about a continuous variable and the standard error of the means, or a binary variable with a standard error on the proportion. As long as you calculate the standard error, then it's the point estimate plus or minus the margin of error to get your confidence interval. Yeah. Oh, I was going to say, I sense I'm starting to confuse people. No? Okay. Alpha is 1 minus your confidence.
Oh, it's 1 minus.
Yeah. Yeah, so if your confidence level is 95% or 0.95, then alpha is 0.05. Alpha over 2 is 0.025. So you would look up the z value for 0.025 unless you use the empirical rule, which is perfectly valid. Yes? The margin of error is half the size of the confidence interval. So it's the amount above and below the point estimate. The range is twice the margin of error. So the margin of error is half of the range. So the confidence interval goes from the point estimate plus the margin of error to the point estimate minus the margin of error. Yes. Let's see. Is there a picture of that soon? Yeah. So in this, the point estimate is, so this would be the sampling distribution. The margin of error would be from the point estimate, which is a z value of 0, up to the positive limit, and also, which is the same as from the point estimate to the negative limit. So you could, on the scale of z, here on the 95% confidence interval, the margin of error is 1.96 in terms of z, and then when you multiply that by the standard error, it gives you your margin of error in terms of whatever it is you're actually measuring. Thank you. So some does and does nots of the confidence interval. Look carefully at this first one. It does not imply that 95% of the population values lie between these limits. So if we're talking about you know, the mean height of Hunter College students and we give a 95% confidence interval, does not imply that 95% of the students have a height in that range. Does that scream out at all of you of, oh my God, no, that's a horrible misinterpretation of the confidence interval? Because it should. It's only to do with our uncertainty in the mean. Nothing to do with the individuals or the proportion of individuals, right? It also does not account for bias in the point estimate. So it accounts for sampling variability, for the amount that that average will vary from sample to sample. But if it's somehow biased because your professor has a young face, it doesn't account for that. But a couple things it does do, proper interpretations. It provides an interval in which we're 95% confident that the true value lies. That's a good interpretation. And also, if we were to take a large number of samples, 19 out of 20 of them would result in a correct confidence interval that contained the true mean. Let's see, Sarah has a question. I thought the z-score did imply that 95% of points were between those points. Okay, so we've been using, up until this point, we've been using the standard normal distribution and the z-scores for populations and for individuals. And for those problems, yes, a probability of 0.95 on the Z table implied that 95% of the population lied within that range. We're using it for something different now. So it's the same distribution, it's the normal distribution. This is a different application. So when you use it to calculate a confidence interval, it does not refer to the number of individuals in that range. Anyone want to say why? Yep. Right, the points on the distribution aren't individuals. It's the sampling distribution. And you remember it's different than the population distribution because its standard error is the standard deviation divided by the square root of n. So it has to do with the distribution of a bunch of samples, not the distribution of a bunch of individuals. Does that answer your question, Sarah? So remember that this population mean, it's something that we assume is fixed and there's some true value for, but we don't know it. So like the age, there is a correct answer, but you don't know it. If we're talking about serum cholesterol levels and the average serum cholesterol for men in their 40s, there is some true value for that mean, but if you only get a small sample of individuals, you can only estimate it. So it's not a random variable. It doesn't have error. It doesn't have variance. It's just a single value. It's the answer. By the way, this is a frequentist. I don't know if any of you you probably haven't been exposed to enough statistics to hear about frequentist versus Bayesian interpretations, but this is a very frequentist interpretation, which is what I am. for the most part. In your assumption, there is some true value, and you're trying to estimate it. And again, if we took repeated samples and constructed a 95% confidence interval around each one of those sample means, then 95% of those intervals would contain that true population mean, and 5% would not. They would be an erroneous confidence interval. Here's what that looks like. These are actually done by a simulation where I drew samples of a fixed size from a normal distribution with known mean and standard deviation, and constructed a confidence interval from each one of those, and put in red here the ones that did not contain the correct true mean. And it's about 5% of them, because these are 95% confidence intervals, about 5% of them failed to capture the true mean. All right, so I'm going to keep on beating on this just to and try and get a few new, see if we can get a few new people to answer questions here. So is the 99% confidence interval going to be larger, or is it going to be smaller than the 95% confidence interval? Larger. Yep. So as the size of the confidence interval increases, does the confidence increase or decrease? Confidence level. Yep, it increases. So the bigger the confidence interval, the more confidence you have in it. Yes?
Well, before you said the 50%, as it was bigger, the person was less confident in that.
Right, that's this kind of different meaning of confidence. Yeah, what I prefer to say is that person has less information about the true answer. Yes? Yeah, so as for a higher confidence, so in the first one, the higher confidence interval is larger, and then the second one is just asking the same question. If the confidence interval is larger, then your level of confidence in it is greater. And you can imagine that on this last one, these confidence intervals are all centered around the mean of that sample. If we were to double the size of these intervals, there would be a lot fewer of them that failed to capture the population mean. So you'd be more confident that you're capturing the true mean. So the key thing here, if you're a betting person, it's in a way less important that you know precisely what the answer is, but that you're able to correctly estimate how confident you are in it. Because even if you don't have a lot of information, as long as you can give an interval where you know pretty well what the probability of being correct is in that interval, then you could place an accurate bet, as long as you can find a sucker who is less good at estimating that than you. Poker face would help. What's that? Right, the payout is bigger when the interval is smaller, because you have less chance of being right in the face of a fixed amount of knowledge. Yeah, if you're going to bet that, in the Super Bowl there will be between 23 and 25 points scored, that's going to be a big payout if you're right. Whereas if you bet it'll be between 10 and 100 points, that's not going to be much payout. I'm not going to go through these in class, but you can, they're here for you to try out. In each of them, you'll have more of these to try. You're given a sample mean. Here's an n so that you can get the confidence or the standard error, and then you can convert that, the standard error, into a margin of error and calculate the confidence interval. All right, so let's wrap up this example. Here are the actual values, the guesses, with the plots. So I calculated from these. This is the mean of the point estimates. So the mean guess was 37. And this is how we would calculate a confidence interval using the methods that you're learning and that you're going to practice in your assignments in the lab. We can calculate a standard error. This is the standard deviation divided by square root of 6 of n, that's 1.1. Using this 0.67, this is not strictly correct. You should be using a t distribution here, but we haven't learned it yet. So I just did it using z. It turns out it's, well, for n equals 6, it'll be pretty different. I'll do it the other way next class, and you can see how different it is. But using that, I calculated the margin of error. So using the intervals that you gave, just taking the average of the minimums and the average of the maximums, I got a confidence interval of 34.5 to 41. But using the point estimates and the z table, it's actually much smaller, 36.4 to 37.9. Which is kind of interesting because it means that for all of these large intervals that you gave, the spread in the point estimates is not very large. Like, they're only between 35 and 41. The margin of error based on the point estimates is only the 50% margin of error is like, what is this? 0.75, twice half of 1.5. And for the 90% confidence intervals, it's good. You see it is a bit larger. I took this to mean that there's a bit of a deficiency in your odds settings, in that the 90% confidence interval is really not much larger than the 50% confidence interval. Just taking the averages of these, there probably should be more difference between them. And when we do it using the point estimates, this goes, so the range here is 1.5, the range here is 3.5. So the 95% confidence, or the 90% confidence interval, is more than twice as big as the 50% confidence interval. And the answer, I'm 41 years old. I am. So thank you. And I am curious to, I hope there were, now that you've been in class, I'm not going to be able to use any responses that come after now, but any that came in up till now, I'm going to use for a 2-sample test to see whether I'm aging or not. All right, and I think it's time for you all to get down to lab. Thank you.
Mm.